Hi, this is problem 11 from the AMC 12A. Looks like a Venn diagram problem, so let's see what we have. Each of the 100 students in a certain summer camp can either sing, dance, or act. Some students have more than one talent, but no student has all three talents. There are 42 students who cannot sing, 65 cannot dance, 29 cannot act. How many students have two of these talents? So again, this looks like a three-category Venn diagram problem. And when you're working with these types of problems, you can work in one of two equivalent forms. One is a algebraic form that we call the inclusion-exclusion principle, and the other is a picture form that we often just call the Venn diagram. Now, whenever possible, I try to work with these pictures. That's a little easier on my brain, and we'll go ahead and do that in this problem. And one thing I noticed from this problem statement that's important is that no student has all three talents. So in working with these Venn diagrams and the three overlapping categories, we'll notice that the center region, the overlap of all three categories, will be 0 for this particular problem. And that'll become important as we'll see. So let's go ahead and try to draw ourselves a Venn diagram. Now, since the center region is 0, we can kind of draw this as a shape of a donut. And I find that kind of helps me visualize what's going on. So let's go ahead and do that. So let's draw out the region set for the students who can dance, students who can sing, and the students who can act. And inside that, let's draw a smaller region of the students who can only act and not have any of the adjacent talents. Students who can only sing and students who can only dance. And for the overlap, we'll represent that with X, the students who can sing and dance, Y, the students who can act and dance, and Z, the students who can act and sing. And so now we can deconstruct the information in the problem statement pretty quickly. So we know we have 100 students in total, so the sum of these 6 regions has to add up to 100. So let's write that out. X plus Y plus Z plus A plus D plus S is equal to 100. And we have these other statements that 42 students cannot sing. So what does that mean? So we have this region here of students who can sing, and the region of students who cannot sing is A plus D plus Y. So let's draw that out. A plus D plus Y is equal to 42. And 65 cannot dance, so that's A plus S plus Z. They cannot dance, that's 65. And 29 cannot act, so that's S plus D plus X. 29. So right off the bat, we see we have 6 variables and only 4 equations. So it's pretty clear at this point that we're not going to be able to solve for X, Y, and Z individually and just add them up at the end. We're going to have to try to solve for X, Y, and Z as an algebraic group. So let's see how we can do that. So one thing I notice is there's some symmetry in this equation set, the bottom 3. So let's go ahead and just add up these bottom 3 equations. And we pick up 2 A's, 2 D's, 2 S's, and 1 XYZ. So that works out to 2 times A plus D plus S plus X plus Y plus Z is equal to 42, 65, 29, 136. And okay, so now I really see a good opportunity here. We have this grouping XYZ, we have a grouping XYZ, we have this grouping A plus D plus S. So I see an opportunity to take the top equation, multiply it by 2, and subtract the bottom equation, and that'll cancel out the terms with A plus D plus S. It'll leave 2 times this term minus this term, which is this X plus Y plus Z. And so we basically see now that X plus Y plus Z is equal to 2 times 100 minus 136. So that's 200 minus 136, and that's equal to 64. And that's our answer, E, 64. Anyway, a good example of three-category Venn diagram problem, and we'll see you at the next video. Bye-bye.